So thank you very much. So maybe I will spend a few seconds to explain who I am. So I spent my last 7 or actually 8 years almost at Elastic. So from Elastic I moved to Vespa. So my background is pretty much about data analytics and search. So today we'll be talking about how Vespa actually can be bound to different topics in AI, actually in the search, and also how to mix it with the LLM features as well. So we'll see how much actually of this kind of considerations you got in your projects or work. But maybe I'll ask a question. How many of you actually heard about Vespa? So pretty much everyone. So that's perfect. Thank you very much. So I was actually thinking that that will be best if we start from demo, and then we'll explain how demo works, and then we'll go deeper into Vespa capabilities. So I'll quickly switch to the demo, and then I'll explain later actually how all of those features are working in Vespa. So this is e-commerce demo platform, which was built actually in a couple of days. So how this actually is divided. So we have a front end built-in lovable, so you'll see actually how this is working. And the back end actually fast API using Manus. So I'm not sure how many of you actually started developing with AI tools, but this is the result of a couple of days of development. So what we see here actually, we see e-commerce products where actually the representations of them were generated through the LLMs, and then also the descriptions are generated with the LLMs directly from the images. So what we actually see here is like Tensor Sparse vector representation actually here from the visible features of each of the item. So when you think actually about these representations, how you generated them or how you got them from the products in the past without the visual models, it was very difficult actually to get them. So clip models or even manual descriptions. So now we can actually do that very effectively with LLMs. So looking into the descriptions, also these descriptions are guided through the LLM. So basically generated from the image, they can have influence from the user-generated content, also category or categorical fields actually which you have in your documents. But then those may be actually acting much better than actually when people are writing something they don't know how to write, right? So basically this will improve overall retrieval and then accuracy as well. So now, very, very simple actually thing here. So I have personalization switch, which actually turns on different ranking profile in Vespa. So now when I turn it off, it's just basically working on the simple one, which will actually show the documents as they are in the results. But what actually is interesting here, that I'm using this vector representations and matching from the document to other documents. So basically similar documents or similar content, which is actually inside our repository. And then as you see here, basically it's feature-based comparison. So all these shapes and look of the products is very similar here. So if we go actually to the product itself, you see that all of these, let's say, t-shirts have images, different maybe colors, but still very similar to each other. If I go actually, for example, here, you'll see that there are some actually kinds of similar, let's say, like even here, similar types of the t-shirts without sleeves and so on. So now, how we actually can change this, actually use this kind of approach in recommender system. So imagine that each element has its own representation in tensors, or actually in sparse representation. So when user interacts in particular ways, so it can click, it can add to the basket, or he can buy the product. So based on these different signals, we can actually transfer portions of that representations into user features. So actually I did in the demo just simple buttons actually to represent those actions. So either thumbs up or thumbs down to add or remove. So we'll switch actually to something which will be more distinct from what we see here. So I would just put gold shoes. So as you see here, we have different shoes which are having different gold components, right? So again, maybe I will show a little bit of how this is actually matching the similar components on different sole types, different shapes. If we actually look here, we have also all flat soles. So it does pretty good job on that. So now I will actually say that I like this component, I will like this component, maybe this one, so focus on the high sole shoes types. Now I can turn on the personalization. You'll see that those are going up front because this is usually, actually this is already changing the personalized vector, which is actually generated and updated actively in Vespa in real time. So now if I actually move back to this view and then I will switch, then you see that you have already personalized base actively when users actually is interacting with data, dynamically it updates per user, not per groups, not with the delays, but just in the time when user is interacting with this. But then let's do other experiments. So let's go actually to user profile and see actually how this is represented based on collections of features. I don't know how this is visible. So you see that actually some features were passed to the user, so sparse features. I did a limitation here. I will talk about algorithm. It's also very simple how this is actually passing those parameters here. And then you see that we have all of them explained. But let's actually change gold. So I remove gold and we'll add black. And black will give higher value 5. So I'll add this and then I will save it. And then I will move back to the representation here. So now you see that everything changed to black and black component. So now when you think about traditional approach for filtering data, for actually faceting and how users are interacting. So in most cases, they can actually say, okay, I like to have blue or the particular brand, particular shape, but it was not really possible in an easy way to do this kind of filtering based on, I like a little bit black and a little bit of green, but not red and not white. So well, let's do that kind of experiment here as well. So I will clean up actually user profile. So this is removed, and then let's do something like black. It will be 5, green, let's do it 3, pink -1, or maybe -5. Then we'll save it. And then let's see actually what's the results now. So now we see that the combination of colors, which we actually mentioned here with different ratios, they are actually visible here. So obviously we can manipulate any type of visible feature from the component which is here. So now we've been actually, so that will be something which I will be adding to the demo, that you can actually also decompose the query from the user. So there is model, for example, very recently actually put on the market, which is called Osmosis 06B, which is pretty fast. So you can actually get the features from the user query, actually make dynamic facets, and then basically enable user, for example, to manipulate facets which are generated actually with the weights, up and down, how much they like those elements, and then you can transfer it to the sparse representation and then use it for search. So effectively, this is how quickly you can do the recommender document. So this is a very simple example, just built to actually show you the concept here. But obviously, when we go to production, we can consider moving to much more complex logic. For example, the per category personalization, then also the user behavioral mapping, so which is called Ocean model, which Cambridge Analytica use for Facebook things actually when they actually been able to understand the behaviors of users. And then you can combine all of those vector or tensor representations in just in ranking profile, and then basically you can get even more and more results in terms of user preferences and user choices for the products itself. And then, of course, when you actually do that in the tensor representations, this will be run on the performance, high performance scale, so you can actually use it in production on hundreds of thousands of queries per second, because this is a very simple sparse vector operation, dot product calculation. So let me actually go back to the little more explanation. So basically, how this was done. So effectively, there is a simple prompt actually for that we are talking to, actually we are generating the content to the LLM as a prompt. So to be a specialist in the fashion area, and then describe all the visible features and then what will be attractive to the, let's say, customer of that e-commerce shop. So it creates this, I would say, pretty nicely designed descriptions which are avoiding known pitfalls from the users who are not knowing how to write descriptions. The other thing is also, and that was actually using Lava model. Lava model, I chose Lava model because it was very cheap and not that slow actually on laptop to generate from a few thousand images, actually descriptions. So then sparse representations of the items was actually done through the GPT-4o. So it also been not very expensive, just few dollars, not even few dollars, just few dollars actually for thousands of documents. And then it was guided to actually generate clean, let's say, JSON documents with predefined keys for the features. Because if we didn't predefine the keys, which is limiting the, let's say, fantasy of LLMs, then basically we got actually much more defined space for this sparse representation. Otherwise, it was like thousands into each dimension, and then you couldn't actually predict what will be across thousands of the documents, and then you actually got for the same color different variation of that color. So it has to have limitations actually. How to actually define those. And then it's actually too much actually to show now, but if you come to our booth, then I can show you exact prompts which I was using for that. So then you can replicate that kind of concept. So now, how the personalization features are transferred to the user profile. So basically, it's very simple. This is just a couple of lines code in Python. So we have user tensor. Then there is decay function. Decay function is actually lowering the meaning for the existing tensor with the interactions, because we don't like the user to stuck in the first choices, so the choices will be actually going with them. So the more he interacts with items, new items, then the more it will be shifting to this new thing. Then we have adding and removing the tensor from the item tensor values. Then there is L2 normalization, so none of the features will go too high, basically, because when we have, for example, black color, which is present everywhere, it will be over-collecting that color, that feature actually with many interactions, so it can grow too high, and it will be actually breaking the results. So L2 normalization has to be done here. And of course, still with the LLM generation, we got a really vast amount of different keys for the features, so we need to limit that to a certain number. So my limitation was 200 features actually for the representation. But then actually important to notice that I did that for any type of product. So t-shirts, shoes, whatever that is in the system is actually the same sparse representation. So I think from production perspective, definitely separating that to categories, and then creating additional sparse representations for how basically much of particular t-shirts, so that will be weighted in the other sparse representation, what's the proportion for interaction with different elements inside the data set is done to represent the diversity of the product groups. And then we can actually put that into ranking also, into directing how the responses will be shaped as well. So this is the amount of code which was written actually to do it. So as you see here, this is the weights calculation. This is actually adding those weights, L2 normalization, and limiting the component, actually number of elements in sparse vectors, actually the dimensions. So not much actually from that. If you look at the previous recommender systems which actually got similar behaviors, it was much more code and much more complex to do the same, right? But we offloaded a lot of work to the LLM ability to recognize those features, which was very difficult in the past. Even clip models will actually focus on much broader scope and not really human readable and defined features. And it's very hard to get that representations otherwise. So I'm really thinking that this is a pretty nice way actually to do. So now how Vespa ranking is done. So probably many of you use Solr and expressions in Solr. So how Vespa is actually looking. So you can see here that we have, this is the definition of the fields. So this is tensor type. So you see the tensor type float, and then we have features. So this is representation of our tensor sparse vector inside Vespa actually for those personalized features. This is a representation for very standard model E5. and then how embedding is done in Vespa. So you have tensor representation, float, then dimensions, and then how this will be indexed, and then so that will be actually taking input field description, embedding, it will be using E5 embedder, which is configured in Vespa, attribute how this is stored, and then indexing in HSNW and then HSNW parameters. So you can obviously configure more things here, but just an example how this data set is done. And now there's the first personalization page. Feature, actually the functionality is actually embedded here. So also not very complex actually from that perspective. So what we have here, we have input from the query. So this is element which is passed from the query to ranking profile. So that's personalized vector. And then this is first phase in ranking. So we have, I don't know if you can read that and everybody understands that. This is very popular thing, which is express in Vespa tensor operators dot product. And then how query is done. So query in Vespa is done in very similar to SQL expression here. And then you have ranking features actually which we pass. And then basically ranking, basically this, let's say vector which is passed here. So Vespa enables you to actually pass anything into the ranking profile. So unlike I would say the Lucene-based systems, Vespa has precompiled ranking profiles into the C execution by binary code. But then what we can do actually to manipulate different components in Vespa, for example, boosting particular elements or changing behaviors, this is how what we achieve through the passing of the features from the query to the ranking profile. So this is personalization search. So when you actually saw when I was looking for the gold shoes, so that's combined with the lexical and semantic search. Actually, this is lexical semantic search. So you have two vectors passed actually here. So we have a query, and then this is the E5 representation model. This is those are our features, personalized features. So just those two components actually to make it simple. Then you have the normalization function for BM25. So we don't like to have scores beyond 1, basically, because when we actually look at the closeness will be from 0 to 1 in Vespa, because this is not the distance, but 1 divided by 1 plus distance. So basically it goes from 0 to 1, actually maximum stuff. So we need to have that in the same space of ranking. So this is how basically the combination between BM25 and then the sparse, so that's normalization. Yes, and then this is actually closeness and description field embedding, and then the global phase we do this personalization re-ranking based on the distances, actually dot product from the documents. And then this actually influences the final result. So first is the search, typical, which we normally do, and then it's a re-ranking phase, which organizes documents in the format that people actually have those which they selected in the past more will be obviously ranked higher. So now I will actually switch to the history of Vespa, because I'm thinking that probably a lot of you actually heard about Vespa, but I will try to repeat that for those who actually hear. So Vespa is not basically new company, actually new product, let's call it like that. It's a new product on the market. It has more than 25 years of history. It was started at Yahoo. So in 2011, actually, Vespa became a standard platform for many of the Yahoo projects. Around 150 different projects in Yahoo are running on Vespa. Then actually Vespa team noticed that tensors, actually not even vectors or not vector searches, but tensor operations will be something for the future. So TensorFlow at Google was probably around the same time when it was created. So Vespa adopted the tensor operations, which enabled Vespa users actually to do more advanced things in ranking, recommendations, and then more advanced search expressions. So in 2017, Vespa became fully open source. So it's Apache 2 license. In 2021, Vespa created the cloud. For those who actually would like to have managed solution, then you can use Vespa Cloud. And then basically now Vespa is going with the newest trends, and basically it is very easy for Vespa platform to be adopted to the new features. So for example, adding the LLM rack components is just new component which you can also develop yourself. So this is just a searcher component, so a couple of lines of code, and you can have your custom logic in the searcher. We have prepared actually examples, so you can actually take it and you can build those searches. And usually when building custom components in Vespa make a lot of sense, is that you can expand or actually move the features from outside of the system inside Vespa, so then processing is close to the data as well. So you actually save a lot on the data transfers and latency as well from that perspective, that you do more calculations, more things inside Vespa. But anyways, let's go further in the story. 2023, Vespa actually was created as a company. So probably this is where most of you actually heard about Vespa 2023. You saw probably our guys on Berlin Buzzwords who were talking before. And then we are now here when Vespa actually is popular across very big organizations. I'm not sure if you know that Perplexity backend is running on Vespa. We have Vinted colleagues here, and then they run on Vespa too. And then we have many big projects actually, search engines like Qwant, or for example, bigdata.com, which is actually focused at similar things like Perplexity, but more focused on financial things. So now, probably many of you will have questions. So Vespa is only for the big things. And then my answer will be, not really, because Vespa can run on very small environment as well, if you like. But what the focus for the smaller projects will be is like when you need to use advanced ranking logic, and then you like to express it fast, and then you like to do a lot of connections to different tensors, LLMs, and everything all together. So that's very easy to integrate into Vespa to get very quick proof of concept. So you saw my demo; it was built extremely fast in a couple of days. So basically, if you like to build something as a proof of concept, you start from Vespa. Then actually to scale it to production is just moving that into the big environment, just copying the application package, and it will work in the big scale, really in production. So, and then you can scale it indefinitely, and then you have guarantees that that will work. So now, talking about the Vespa building blocks. So I think what is actually really good at Vespa, from my perspective, looking at my previous experiences and so on. So real-time partial updates is very key actually to do personalization, real-time operations, and so on. So then effective data storage. So that's again something which is, many will think, okay, maybe it's not effective, or maybe we don't know how to do it. So Vespa actually enables you even to create different data structures and data storage types for one single schema. So let's imagine that you would like to have span, let's say, algorithm implemented. So you have the centroids actually in memory to be searchable fast, but then actually related documents which will be related to particular centroid, they don't need to be stored in memory for fast searches, because then they can be actually paged to the disk. So then you have another content cluster for that documents actually to be searchable for the disk. We have actually blog about HSNW IF implementation, how you can actually create that into different clusters in Vespa. So, and then you have really big flexibility on configuring this data effectively. So then extensive ranking framework. So I will talk about how ranking is actually done in the next slides, but then Vespa enables you to put tensor operations and then advanced logic inside actually components. So then again, integrating machine learning components and LLMs. So I'm thinking about models, embeddings, and re-ranking models, because those will be actually the three types of models which we'll be working with. So that can be actually inferenced directly in Vespa on CPU and GPU. So, and then we'll have some new things coming. So look at our website at our news, because there will be even more simple ways of actually implementing LLMs and more complex things into Vespa. And then the last thing, which is actually probably also very nice, is this vast range of customizable components. So if you like to build your own embedder, you like to build your own searcher or document processor, this is just single Java component which you can build and attach to the application package and deploy together with application package as a custom component to the Vespa containers. It will be running for you. So if you'll be interested in seeing how to build that, I also can show you how I built chatbot interaction API just in Vespa component, not outside of Vespa, but just in Vespa as a full API with Vespa containers. And then obviously the things for those who are willing to run things not by themselves, but in the cloud. So Vespa Cloud has auto scaling up and down. We are talking about Vespa container here. So if you don't have traffic or traffic goes down, you can actually scale it down. If you have higher traffic, it will scale up. So orchestration, optimizations. So basically, all of the things actually deployments, and then how you combine models with Vespa is actually embedded into Vespa configurations. When we talk about deployments, actually there are two things, because we are supporting CI/CD, so it's like Kubernetes deployment files. We have Vespa packages, application packages, where you can version those packages. You see how deployments, if they were successful, you can move them from a development component to production with one switch. If you test that on your, let's say, laptop, you take the same package, you just show where this should be deployed, and then it will just work straight away without reconfigurations. So I think this is pretty good about Vespa, that management is very, very convenient. So now, how the Vespa ranking, what was the Vespa ranking profile concept behind that? So we believe that actually, probably I will just make sure that everybody actually is aligned here. But then when we look at Solar probably can do very similar things. But in Vespa, we organize that so this is very human readable. So we have something like ranking features, which can actually go into the ranking profiles. Ranking features are, many of them actually, tens of them are defined in our documentation, so like BM25, closeness, freshness, and many of them actually, which are derived from the documents by itself. So all the lexical components, all the, let's say, elements like weights for different tokens, all of those kind of things will be here. So then we have attribute features. Attribute features are actually coming from the fields, from the data directly. So if you have dates, if you have user profile names, or whatever kind of data, or distance, geolocations, anything can be actually passed from the document by itself. And then we have also query time user signals. So those are the variables which you pass to the query as the tensors or scalars or text. So whatever you want actually to pass here, we can do. Then this is Vespa ranking profile logic. So the logic is written using the arithmetic logical expression, conditional logic. So all of this kind of complex expressions, including tensor operations, can be done actually directly in the ranking profile. And then what will be the output from Vespa? So that will be ranked documents and also runtime generated fields. So we call those fields actually match features or summary features, and then match features are generated on the match phase and summary when you actually generate documents, because documents during the search, similar in Lucene, they will have just IDs, but you need to actually populate those documents with actual fields when actually they are on the summary stage when this will be generated. And also you can generate summary features which will be results of expressions. And quite often these actually match features or summary features will be used by different companies actually to fine-tune the results, because you can actually expose all of those features outside of the ranking profile to the response documents, and then you can use them for, let's say, different models to retrain and then fine-tune the ranking profiles as well on the end. So now stage ranking in Vespa. So why stage ranking is so important, and actually it has impact on the performance or even latency itself. So I'll just go quick. So when you actually think about the search, actually lightweight things can be done in memory on big, vast amount of data. So we are talking about billions of documents, right? But if you try to do Colbert model on billions of documents, it will be probably very slow. So how we need to do that? We need to actually use different methods like BM25, which is lightweight, or smaller models, which will actually do this, let's say, earlier stages, and you actually pass those results to the later stages. And then along of those actually stages, you can also do additional components, like you saw personalization component on top of the final results. On each stage, you can do all the operations. And then Vespa has localized, let's say, ranking per node, and it has global stage, which is actually done on the top nodes, which actually take the results from all and re-rank it on the final stage to actually have combined results from all of the nodes. And then basic re-ranking example. So you see here that we can put attribute, freshness, and then BM25. Freshness is, for example, date of the document when it was published. So we don't like to have old documents. We like to rank higher the fresh documents. Then attribute quality. If we have quality measure in the document by itself, update it. And then this is live updates may be actually important here for quality measurement by the users. Then we can actually use it for ranking, and these results will be live working. So you can use, for example, scoring for the documents also, which will be updated and used in the scoring, right? Then you have models, re-ranking models in this case, so not like embedding models and where we use closeness, but for example, cross-encoders, XGBoosted models, XGBoost models. Those will be used for re-ranking to give the scoring and then filtering documents on different stages. And quickly, Vespa Tensor Framework. So what is actually Tensor Framework? Tensor Framework in Vespa is actually ability to express any tensor format or form inside human-readable expression. So as you see, tensor is basically the standard double. Then you have three-dimensional vector. Then you have here map of vectors, and this is map of sparse representations, which I said for e-commerce might be good to represent categories as sparse representation for those categories. Then uniform tensor model. Actually, by having this clear definitions, really strong type system, we can actually do sparse or dense vector operations directly where the data is. So that's also shortening the path between data and calculations, which is having heavy impact on the performance and latency. And then we have core tensor functions, which actually enable you to do actually virtually any operation on tensor, actually from standard dot product to even neural net definition with ReLU function and sigmoid functions. So basically what it gives you, actually this tensor framework, is that you can express any kind of machine learning model in Vespa just by writing simple expressions. So the good example was, which we've been showing already last year and 2 years ago, is Maxim function to deal with the late interaction models like Colbert and Copali. And then that was just a simple expression with the MapReduce functions actually inside tensor operations. No code change, just the tensor operations. And then this is the last thing which I'm showing actually today. So this is the example how you can treat chunking. I'm not saying that this chunking is the, let's say, perfect way, but focus on what happens here in tensor operations. So we have actually chunking tensors per chunk, and then we have chunk array. And what we actually do here, we calculate BM25 automatically with one expression for each chunk, then scoring per each chunk, actually distance, then scoring for each chunk. Then we combine those two, BM25 scoring and scoring for the similarity scoring. And then we select the chunks which are having the best scoring from both semantic and BM25. And then we are able to select and return to the document to the user only those chunks from the document, not full document, across many documents, only those chunks which are having the highest relevance to the result. So effectively, you are not sending everything as a result from the bigger documents, but only chunks which are relevant. And that's it. And then maybe you have some questions. So this is a link to our website where you can actually get the content as well. And then one more word we have here, our partner Searchplex. If you have any questions to Ravi, then you can actually find him, so we can split answers if you have more. So any questions?
First of all, thank you so much for Piotr. I think he deserves a round of applause, so thank you so much.
Thank you.
And we do have a few minutes for questions, so any questions either online or from the folks in the room? Yeah. Like that.
So when we are re-ranking, 3 phases re-ranking, right?
Yes.
So in the first phase re-ranking, are we taking the user input as in?
So in the demo?
Yeah.
No, so actually user input, it will be user query. So that was actually BM25, for example, or closeness. It depends if semantic or BM25. So you do a very traditional, let's say, ranking as normally you will do. But the last stage, basically that was personalization re-ranking based on the user liking basically what was actually passed to his profile. But obviously this is just an example of your implementation. What will be best actually can be experimented. If that's better actually to do similar to reciprocal rank, that you put everything in global stage including semantic and BM25, or you actually put any other signals, for example user rating for that product and many other things. You can input that as well into ranking profiles to influence that, or maybe even how much revenue you get from the product, because maybe that's important for the company actually to rank higher products where the revenue is higher and they are having similar look, right? So you have similarly looking items, but then revenue for this is $10, for this is $2. So what you rank higher? The one which is looking the same but is more expensive, actually more revenue for you, right? So then you can implement this logic inside Vespa very easily.
So in the first phase, like when we are doing the BM25, right? So is there any chance to lose the semantic context?
So in BM25, so we know how BM25 works, right? So it will be having much smaller recall than semantic. But what semantic is actually doing is introducing sometimes noise. Because when I have description like this is beautiful summer t-shirt with something which pairs very good with this, let's say, open shoes. And then I look for the shoes, I get a t-shirt. So that's semantic, right? Then we need to fine-tune heavily. So fine-tuning, you know how to do fine-tuning with different parameters from the lexical world. And then when lexical part is actually good, then you can actually limit, let's say, this into the particular space. But also I got another consideration, so we've been discussing with people here, that you can use LLM to extract more relevant information and use that for re-ranking as well, as a sparse representation, so you can remove the noise. But then it will be higher cost, obviously, for doing that. But then this will have the same problems as typical search, that you need to actually work on fine-tuning to actually get better relevancy and remove those noise actually from your documents. And then I would say that the search is as good as your data. So the more noisy data, the worse results you have, right? So it can be also treated from the perspective that you use LLMs to verify the descriptions and content in your items upfront, that you actually get better search results later on, and then less effort on fine-tuning the search itself.
Okay, cool. Thank you.
Okay, we have time for one quick question. Any further questions? Okay, so okay.
I have a quick question. Like, how do you support people? Like, if I were to migrate from Elasticsearch or Solo today to Vespa, like all my indexes, do you offer like good integrations? How I can do this quickly without re-indexing the universe, maybe?
So actually, how much effort and what will be the changes from? So I would say that this is not for a minute answer. but actually, if you'd like to hear about that, come to our booth. So then we can actually show you ideas, and we have actually. Yeah, so Logstash actually Radu developed Logstash. Yes, so. And then schema definition is something which you can represent very similarly. However, actually queries and ranking, that's what the differences are. So it has to be translated into that, yeah.
Okay, so again, big round of applause for Piotr. Thank you so much.
Thank you.